All right, good morning, everyone. My name is Mo. I'm from Brevis. Today, I'm going to talk about how we are building ZK coprocessor by merging both the ZK proof technology and also cryptoeconomics design. Because this is kind of an academic venue, I'm going to more focus on the technical design part of this, but less focus on the use cases of some of the ZK coprocessors. But before we do that, let's first take a look at what is a ZK coprocessor, right? So we have Ethereum and we have many different blockchains, but they are still mostly rooted in distributed consensus. And therefore, as they are blockchains, the fundamental construct of them limit them to be very bad at data-rich and very heavy computation. A very, very typical example is this trader loyalty program. On every centralized exchanges you guys use today, you always have this capability to receive a trading fee discount if your trading volume in this last month surpasses a certain value, right? But if you look at every single decentralized exchanges, including Uniswap, none of them have that feature. Why? Well, because to implement that, you actually need to have just for one user to get the proof in the smart contract saying that, okay, I actually traded more than $30 million in the last couple of months. It actually requires 4 hours of computation time plus 20K in transaction fee on Ethereum. So why is that hard? Well, this is because there is no way in smart contracts today to actually access these kind of historical data, including historical transactions, events, and states. So in theory, you can do this on blockchain directly by allowing the smart contract to periodically remembering all the state's root. And whenever you want to do the calculation, you first need to calculate 10,000 Merkle proof of transaction inclusion directly on chain. You need to basically repeat all the hash process to essentially expand a succinct block header into all this data you want to access, and then decode the final leaf data on chain as well, and finally compute whatever you want to compute, such as summing all the swap amount to get the trading volume on chain directly, which is going to be a horrible thing. So the result of that is that it is not possible to do this type of thing on blockchain because blockchain fundamentally doesn't have trust-free access to historical on-chain data, and there is no trust-free access to historical data on other blockchains, and therefore it is generally bad at data-driven and complex computation. The fortunate thing is that we had this kind of a problem before in computer history. If you think about the evolution of CPU, right? So like CPU itself, even though its processing capacity is doubling every couple of years, it was really bad at certain type of computation, like float point, like anything related to graphics. This is why we introduced GPU as CPU's coprocessor to offload certain type of applications in the computation that is hard for CPU to do to this new type of architecture, and returns the result when the computation is done. Blockchain, as the Web3 CPU, also needs its own coprocessor, where the blockchain can just focus on transactional computation, while this coprocessor will focus on data-rich and very complex computation. But the key thing here is this. This type of architecture needs to ensure that even with the introduction of this coprocessor architecture, there is no compromising of the trust-free nature of blockchain applications. That is a key point. Now, how do we do that? Well, what we can do here is to use zero-knowledge proof technology to essentially replicate the type of computation that I just mentioned, but move that from blockchain to an off-blockchain environment, do the computation, and generate a zero-knowledge proof, and feed that computation result back to blockchain smart contract. So to put it simply, what blockchain coprocessor or ZK coprocessor like Brevis is doing is essentially it is giving smart contract the capability to access tools like doing the analytics dashboard, right? So if you think about like all these off-chain indexing tools, they are mostly for human eyes. But we're enabling this type of data visibility and computational capability for smart contract, and that can enable a lot of exciting things. So what Brevis is doing is generate ZK proof of arbitrary computation on any data and utilize the computation result on-chain in entirely trust-free way. Developers building on Brevis can simply do kind of a read and compute and verify process, as I just mentioned, that it can basically allow developers to access storage states, block information, receipt information, beacon chain state, account transactions across all these different chains, and in a very, very simple way. So the key thing here is that you can actually write your SDK in a way that it hides all the ZK complexity and the ZK circuit complexity away and allow users to just simply use this stuff. And then you can kind of abstract this data stream into a MapReduce-like construct where users and developers can write their business logic, such as basically computing the trading volume or computing the loyalty program or computing identity solutions. And finally, you can put the data and the application, the result of the computation back on-chain for smart contract to consume and drive their additional smart contract business logic. So when we're talking about ZK, one thing we always ask is that, is it fast enough? Is it low cost enough to actually be actually used in applications? Well, we have some benchmark to share. So, in today's deployment, to prove a trading volume of 1,000 transactions on Uniswap, on a 8 server of very, very typical consumer-grade GPUs, the cost is merely $1.8, and latency is 100+ seconds. To put things in perspective, Uniswap across all blockchains on a monthly basis generate 4 million transactions, and the monthly fee is like 14.7 million. So Brevis, if we are processing every single transactions on Uniswap, we'll have the capability to process 19 million monthly capacity transactions, and the fee cost is only going to be $7,000, which is like tiny fraction of what Uniswap is doing today, what Uniswap's revenue is today. So one thing that I want to really highlight here is that even though that like the ZK is already very scalable and low cost, we also recognize that there are certain application users that don't want to use ZK upfront. So they still want to have the option to have an even lower cost and lower latency solution. And this is where we actually introduce crypto economics design to combine that with the ZK design, and to enable cost efficiency and also key feature support. So the idea here is that we are working with EigenLayer to introduce a Brevis AVS, which is called Brevis Code Chain. So when smart contracts similarly have a co-processing request saying that, okay, how about you compute the trading volume for this user for last month? The request is going to first go to the Brevis AVS, and the Brevis AVS node operators in the AVS will collectively generate the processing result first, and propose a crypto economics validated and secure result on the blockchain first. And an application specified challenge window will start. In this case, if the application does detect a fraud or does detect an issue for the co-processing request, the challengers themselves can initiate the challenge and submit a ZK proof during that challenge period to revert the incorrect assumptions and incorrect calculation result. So this way, we combine the capability of crypto economic security with ZK fraud proof together to build a system with broader trade-off space. So what this enables is not only just lower cost, but one thing to really note is that the type of challenge that you need to do to challenge a crypto economic security proposed result is incorrect is actually going to be vastly lower than doing the ZK computation from scratch of yourself, right? One typical example for that is the proof of completeness or proof of non-existence. So in ZK, if you want to prove that, okay, there isn't a transaction between a user to a smart contract, that is very hard to do in ZK because you literally need to generate transaction proof for the entire history of the block to prove there isn't such a transaction. But using crypto economics proposal plus ZK challenge, things are much easier, where you can have the Brevis ABS propose the fact that, okay, I claim there's no transaction that is involved between these two contracts. And then the challenge process, if needed, is just to prove one existence of a transaction to say, okay, what you're saying is wrong. So what I'm trying to say is that there has been a lot of debates about the crypto economic security and ZK security and how they interact with each other. What we're saying is that they should actually be working hand in hand in certain use cases to allow developers to build more different features and kind of have more trade-off options. So there are a lot of different use cases you can do with this type of coprocessor. To catch up some time for the organizers, I'm going to just focus on one type of application use case, data-driven DeFi. Now, what is data-driven DeFi? Well, if you think about it, when you're using DeFi application today, whether you are a big whale that is trading vast amount, having huge amount of liquidity, or just a knob just starting to use blockchain applications, you are treated exactly the same in the application. There's no differentiation between different users whatsoever, right? So what Brevis and also ZK coprocessor in general can do is that it can take these data input and now allow smart contract to look into its protocol data in the past and figuring out, okay, who is depositing into our LP's positions, who swapped the most things in this, who did most of the liquidations, who has most historical risk, and do this calculation based on this historical data in a trust-free way, and put that data back in the blockchain to drive business logic. One simple example is the dynamic fee based on trading volume, or fee discount based on past trading volume that I just mentioned. We're working with Uniswap for that. And there are also trust-free liquidity, active liquidity management, where these AML solutions can drive users' liquidity to adjust and readjust position based on on-chain trust-free triggers and proof of that. And you can also do retrospective farming reward. Because what we have for farming reward today is that LP deposit liquidity for a certain length period of time, and the liquidity farming reward just distributed to them proportional to the time length of the liquidity deposit. But this is not actually optimal. What you should do is to actually look back and see who actually provided liquidity when the market is volatile, and retrospectively analyze the LP behavior and distribute the reward to them accordingly. There are also things like transfer-free temporal intention-based automation, and just want to touch base on several other things such as ZK reputation, where you use omni-chain cross-protocol action proofs to figure out who are the good users for your protocol and the chain, and give them a ZK attestation of their identity, and let them kind of be eligible for things like airdrops and stuff like that. And also on a kind of a per application basis, you can start to differentiate the users based on their historical behavior in the smart contract without actually introducing any complexity for your smart contract up front, and also have a very, very dynamic way to kind of adjust that. So there are many, many things you can build with architectures like this. But what we want to, again, highlight is that in this kind of academic setting, is that a ZK coprocessor can be kind of incorporated and integrated with crypto economic security to achieve much powerful property down the road. With that, that will be my talk. Thank you.